Hello everyone. Now we are going to discuss the working principle of two cavity Klystron amplifier. It is mainly used to amplify weak RF signals. A two cavity Klystron amplifier works on the principle of velocity modulation. The two cavity Klystron amplifier consists of five major components, namely electron gun, pair of anode plates, buncher cavity, catcher cavity, and collector plates. The first component is cathode, which produces a beam of electron. The second one is anode place, which focuses the electron beam in order to make it as thin beam of electron. The third component is buncher cavity, and the fourth one is catcher cavity. In buncher cavity, a weak RF signal is available which is used to modulate the velocity of electron, and the electron bunch is formed in the space between buncher cavity and catcher cavity. In the catcher cavity only the amplification of weak RF signal takes place. The electron bunch has enormous amount of energy and which is used to amplify the weak RF signal. And finally, the weaker electrons are collected by the collector plates. The applicate diagram describes how the velocity of electron is modulated with respect to RF voltage. The velocity of electron which falls during negative half cycle of RF voltage is decelerated. The electron which falls during positive half cycle of the RF voltage is accelerated. The electron which comes during the zero value of RF voltage travels with unchanged velocity. The major components of two-cavity Klystron amplifier are cathode, anode, buncher cavity, and catcher cavity. Finally, collector plates. Cathode produces a beam of electron, and a pair of anode plates concentrates the beam of electron. Buncher cavity is responsible for velocity modulation. The amplification of weak RF signal takes place in the catcher cavity. Finally, once the electron energy is transferred, the electron bunch becomes weaker and it is collected by the collector plate. The various parameters associated with the operation of two-cavity Klystron amplifiers are: capital V0 is the DC voltage supplied to the cathode, V1 is the amplitude of the weak RF signal, and omega is the angular frequency of input signal. Lowercase v0 is the uniform velocity of electron between cathode and buncher cavity. T0 is the time at which electron enters the buncher cavity. T1 is the time at which electron leaves the buncher cavity. Tau is the transit time. Theta g is nothing but phase variation of the input signal during transit time. Beta is the beam coupling coefficient of the buncher cavity. Once the electrons are generated by the cathode, these electrons will travel with the uniform velocity from electron gun till reaching a puncture cavity. This unchanged velocity of the electron is given by expression number 1, where smaller v0 equal to root 2v capital V0 by m, where E represents charge of electron, capital V0 represents the voltage which is supplied to cathode gun, and m represents the mass of electron. Once the electron enters into the cavity cup, the velocity of the electron is modulated due to the existing of RF voltage, and the value of RF instantaneous value of RF voltage is given by Vs equal to V1 sin omega t, which is represented by equation number 2. When the electron enters the cavity gap, it interacts with the RF signal and the velocity of electron is modulated. The velocity of electron is deaccelerated when it falls during negative half cycle of RF voltage. The velocity of electron is accelerated when it falls during positive half cycle of RF voltage. And tau is the transit time, which is nothing but the time taken by the electron to cross the puncture gap. As the electron stays for a duration of tau in the cavity gap, it is necessary to find the average value of RF voltage for the duration of tau. In order to find the average value of RF voltage, we need to integrate the instantaneous value of RF voltage for the period of T0 to T1. So V average can be written as P average equal to 1 by time period integration T0 to T1 V1 sin omega t dt. After integrating sin omega t, what we will get is cos omega t. Then we substitute upper limit and lower limit. Finally, we will get V1 by omega tau cos omega t naught minus cos omega t1. So from this we can able to write t1 equal to t naught plus tau. So t naught plus tau can be written as d by v naught. Then finally you substitute t1 in the place of cos omega t1. The final expression can be obtained as v average equal to v1 omega tau into cos omega t naught minus cos omega t naught plus omega d by v naught, where omega d by v naught equal to theta g, which is nothing but angular phase shift. As we have seen, the expression for V average is V1 by omega tau into cos omega t naught minus cos omega t naught plus theta g. This is in the form of cos A minus B minus cos A plus B. This can be written as 2 sin A sin B. Here A minus B is omega t naught and A plus B is omega t naught plus theta g. Just by solving these two expressions, we can get the values of A and B. A value is omega t naught plus theta g by 2 and B value is theta g by 2, and V average finally can be written as V1 sin theta g by 2 by theta g by 2 into sin omega t naught plus theta g by 2, where beta I is beam coupling coefficient and that can be written as sin theta g by 2 by theta g by 2. And finally, the expression for V average can be written as V1 into beta I into sin omega t naught theta g by 2. Once the electron enters the puncture cavity, the velocity of the electron is modulated based on the average value of the RF voltage. Now the velocity modulation expression can be written as V of T1 equal to root 2e V0 plus V average by M. By substituting the value of V average in the above expression, now the velocity modulated expression can be obtained as root 2e by M capital into capital V naught into 1 plus beta I V1 by V naught into sin omega t plus theta g by 2. The amplitude of weak RF voltage is very smaller when compared to DC voltage. The effective value of beta I V1 by V naught becomes very smaller than 1. So by using binomial expansion, we can able to write root 1 plus x as 1 plus x by 2. So finally, the velocity modulated expression can be obtained as V of t1 equal to V naught into 1 plus beta I V1 by 2 V naught sin omega t naught plus theta g by 2. But also the transit time tau can be written as t1 minus t naught. From that, omega tau equal to omega t1 minus omega t naught. Finally, omega t naught plus theta g by 2 can be written as omega t1 minus theta g by 2. By substituting these two things, we can able to get the velocity modulated expression in terms of T1 as well as in terms of T0, which is represented by expression number 6 and 7. This diagram demonstrates how the bunching process takes place after the velocity modulation process. The electron which falls at the time period Ta is deaccelerated because of negative RF field. The electron which falls at time Tb travels with unchanged velocity due to zero RF voltage. The electron which falls at time period Tc is accelerated due to positive RF voltage. All these electrons meets at one point at time equal to Td and the electron bunch is formed. This electron bunch has enormous amount of energy which is sufficiently enough to amplify weak RF signal. An electron bunch is formed at a time t equal to Td at a distance of del L from the puncture cavity. So del L can be written in three different ways. Del L equal to V minimum Td minus Ta. This is first one. Second one is del L equal to V naught into Td minus Tb. This is second expression. Third one is del L V max Td minus Tc. Now we need to represent Ta and Tc in terms of reference time period Tb. So del L can be written as del L equal to V minimum into Td minus Ta equal to V minimum Td minus Tb plus omega pi by 2 omega. Similarly, another expression also can be written as del L equal to V max Td minus Tc equal to V max Td minus Tb minus pi by 2 omega. As we know that modulated velocity of electron V of T1 is written as V naught into 1 plus beta I V1 by 2 V naught sin omega T naught plus theta g by 2. This omega based on the value of omega T naught plus theta g by 2, either the velocity can take maximum or it can be minimum. Whenever the value of omega T naught plus theta g by 2 is 270, the velocity is minimum. Whenever the value of omega T naught plus theta g by 2 equal to 90, the velocity is maximum. So the expressions for V max and V minimums can be written as V max equal to V of T1 V naught into 1 plus beta I V1 by 2 V naught. The minimum velocity is written as V of T1 in equal to V naught into 1 minus beta I by 2 V naught. By substituting equation 13a in 12a, we can get equation 14a. Similarly, by substituting equation 13b in 12b, so we can get 14b. As the left hand side for equation 14a and 14b are equal, whenever we subtract equation 14b from 14a, we can get left hand side as 0. Then by simplifying, we can able to get Td minus Tb equal to pi into V naught by omega into beta I into V1, which is shown by equation number 15. By representing time period in terms of distance and velocity, we can able to write Td minus Tb equal to del by V naught. From that, del L can be written as lowercase v naught into pi capital V naught by omega into beta I into V1, where del L is the theoretical value of distance between puncture cavity and the point at which bunch is formed. However, in order to get the maximum bunching, the optimum distance should be L optimum equal to 3.682 lowercase v naught into uppercase v naught by omega into beta into V1. In order to find the bunching parameter, it is necessary to find the time taken by the electron to cross the trip space, and which is given by capital T equal to capital L by V of T1. So in the place of V of T1, substitute the modulated elasticity expression. Then by using binomial expansion, we can able to write 1 plus x power minus 1 can be written as 1 minus x. For x is very less than 1 and v naught is very less than v1 is very less than v naught, then we can able to get expression number 19. Then by multiplying omega with the equation number 19, we can able to get expression number 20, where omega into t naught can be written as theta naught, which is variation in the signal phase during the time period t naught. Then we can express omega into capital T as theta naught minus x sin omega t1 minus theta g by 2, where x equal to beta I v1 by 2 v naught into theta naught, where x is called as bunching parameter of two cavity Klystron amplifier. In order to get the maximum energy transfer, the electron bunch has to enter the cavity during negative peak of the RF voltage. So the above condition can be expressed as theta naught equal to omega t naught, which is equal to 2 pi smaller n minus pi by 2, which is equal to 2 into pi into capital N, where smaller n is the integer and capital N is the number of cycles the angle is undergone changes during the transit time. I hope you guys have understood the working principle of two cavity Klystron amplifier in detail. Thank you.